Now I'm going to talk about deformed and doubly special relativity, which has been mentioned a few times. It was nice of Stefano and a few other people to mention it. And what I'm going to talk about particularly is an issue of non-locality in it, which I hope I'll convince you is a severe issue. It's not a new issue. It was raised over the years by various people. Recently, Sabina raised it in a very vivid way, as I'll discuss, and it's been the subject of some interest and some attempts to understand since then. Unfortunately, or maybe fortunately for the point of view of the audience, but unfortunately from the point of view of the speaker, what I'll present is some steps towards resolution of the issue, but not a complete resolution. So you can take that as an invitation to jump in from whatever point of view and try to resolve the issues, but not to jump in during the presentation. Let me at least try to make clear what I think is understood and not understood. And I have thanks to many people that I've been involved in discussions with this about, particularly Sabina, Giovanni, who will be here tomorrow. But I want to mention especially Jurek Kowalski-Blitzman and Michaela Arzano, because much of the substance of what I'm going to say is based on material from them, which for better or worse is still posted on the archive. But I will be relying on their work, and then a number of other people. And there's some recent papers if you want. Now, this is an idea which is by at the moment about 10 years old, although in the mathematical versions were anticipated by a number of years. But let me approach it from a point of view which is due to Jurek Kowalski-Blitzman, which I think is very illuminating. It's the most illuminating. We just imagine there is some quantum theory of gravity. I think most of us hope that there is some way to understand nature which unifies C, h bar, and Newton's constant. Okay. We're used to thinking about different limits. We're used to taking the limit in which Newton's constant goes to 0, which is quantum field theory, with h bar and c. We're used to taking the limit when h bar goes to 0, which is general relativity, which is g and c. There's another limit that, if the theory is well defined, must exist, which is h bar goes to 0, Newton's constant goes to 0, but the ratio fixed. And the ratio, and I use units where the speed of light is 1, since I don't touch the speed of light, where the ratio is a mass or an energy, which is the Planck mass. So imagine from whatever is the right physics, taking the limit where we turn off quantum mechanics, we turn off gravity, but we keep a kind of smile of the Cheshire cat of quantum gravity, this scale fixed. There should be such a physics. Okay? It's an experimental regime with two constants, the speed of light and this fixed mass scale, the Planck mass. Okay? I want us to think about it as phenomenologists. What's the phenomenology? Already a question.
Can I ask a very nice question?
Yeah.
So what do you mean by a regime? Is that energy or regime, or because
good. I will address that very precisely. You'll see in a minute.
Okay.
Okay? Okay. But I'll be vague for this transparency. This is a regime with two constants, c and this new constant, Planck mass. Without this, it's just relativistic dynamics of point particles, or classical relativistic dynamics of fields. But what is it if we include this constant? Okay. And particularly thinking phenomenology, what is the symmetry algebra that governs this phenomenology? In particular, is it Poincare symmetry, which is the symmetry with just C that we believe in? Is that symmetry perhaps enhanced? Perhaps it's enhanced to by some kind of conformal or scale transformations. Is it broken, as we've been hearing in several talks about the phenomenology of breaking of Lorentzian breaks, in which this would be the breaking scale? Or is it perhaps deformed? And deformed is the idea that deformed special relativity tries to investigate. What deformed means is that there's still a symmetry algebra which has 10 generators, but has this scale in it. So a very useful way to think about this, I think, is to start in momentum space. Okay. And why am I starting? And this is an answer to the question of what, okay, what regime, what K. Why I start in momentum space is first because there's a simple idea about momentum space, but also because, as I'll emphasize later, okay, the constant of the Planck mass is h bar over g and goes to a constant in this limit. The Planck length is the square root of h bar times g and goes to 0 in this limit. So any phenomena associated with a length or a time is invisible in this limit. So I just want to talk about momentum and energy because this Planck has dimensions of momentum and energy. And the question which underlies the whole talk and the whole issue of locality is what is space-time. But before we talk about what is space-time, let's talk about momentum space. Okay. So a hypothesis, a simple hypothesis, is that here we have a parameter with units of mass. We want to deform momentum space. We want to deform relativistic physics somehow. So let's deform the geometry of momentum space. Let's imagine that momentum space is curved, and this is a measure of its radius of curvature. There's then, roughly speaking, two possibilities. There's a generic case, in which case, so momentum space has a 10-parameter group of symmetries, which is the Poincare algebra. Okay? If we generically curve it, we break that symmetry and reduce the number of symmetry generators. But notice that we can curve it with a constant curvature, take it, say, to be de Sitter space-time, and we still have 10 generators. That is, the symmetry algebra are now the generators of the de Sitter group symmetry. Yeah?
Just a philosophical question. So you assume that momenta are more fundamental than coordinate of these states?
Yes.
Or?
Which is good.
Or at least more fundamental, meaning less problematic, as you'll see. Okay? So momentum space, now think of as de Sitter space-time. The Poincare algebra is deformed to the de Sitter algebra. You have 10 parameters, 3 rotations, 3 boosts, and 4 translations. What are the translations on momentum space? Well, if you think in terms of Poisson brackets or equivalently in terms of commutators in quantum mechanics, the generators of translations on momentum space are the space-time coordinates. So these generators of translations on momentum space are going to be the space-time coordinates, and because the momentum space is not only misspelled but curved, the space-time is non-commutative. And this is a point that Sean Majid has been making his whole career. It goes back to his PhD thesis. Okay, and he deserves credit for this fundamental idea. Okay. We're used to thinking that momentum space is flat and space-time is curved. Sean's point of view is that let's start off asking what happens if momentum space is curved, and start there, okay, in a kind of dual picture. And it's possible to pick coordinates, that is, pick the exact translation with which exact 4 of the symmetry generators on de Sitter space you're going to call the space and time coordinates. You can choose them in such a way, and there are a lot of details about that in this talk, but such that what you call x and what you call t have this commutation relation. X with t is the Planck time times x. Okay.
So is that for any deformed dispersion relations, any deformed?
No.
Specifically for
this is a specific choice. Okay. Okay.
So it is regime that's 0, as you said.
Yes, good. Good. Okay. If I had written Poisson brackets, it wouldn't be 0, but I did write commutators. And I want to emphasize that when I write commutators, there's an h bar here. Okay. And so in the regime, strictly speaking, that I talked about, this is not there. Right. which you can say another way, which is if you want to introduce space-time as the dual of this curved momentum space, you would really like to have an h-bar around, okay? And then you have to do quantum physics. Okay. And none of what I'm saying is new remotely, but this is really an interpretation of things that have been in the mathematics and physics literature on this subject for some time. Okay, so this is just a summarizing my philosophical point of view, okay, and I'm taking this point of view to a word that people in humanities love to use to problematize something that is to focus our attention on, which is what is space-time. Okay. And I'm taking the point of view that we could do physics in momentum space, so I could just start to write down some Feynman diagrams in momentum space and propagators in momentum space and vertices in momentum space, and I could do physics in momentum space invariant under the de Sitter symmetry. I'm not going to do that because the purpose of this talk is to focus on the question of what is space-time. And the point of view is that we start with momentum space. Space-time is derived as a dual. Or from the point of view, if I were sticking to the classical picture, I would say I construct a cotangent bundle on this curved momentum space, and that gives me a phase space. Okay, but this is really what I just said in answer to Daniel's question. And hence, it's most natural because if I want to see some deformed physics that has something to do with the Planck length or the Planck time, okay, I'm going to take the point of view that because h bar is there, that I have to address that physics quantum mechanically. That's, if you like, a hypothesis. Okay. So the point of view is momentum space, then the phase space, then space-time. And let me raise an issue. Okay. If we think from a phase space point of view, there's a remarkable thing about special relativity, which is that the transformation properties of a world line, okay, a world line carries energy and momentum, and a world line also is at some particular points in space and time. But the transformation properties of a world line are independent of the energy and momentum that they carry. So you can abstract from the phase space down to space-time by forgetting, let me back up. Let me be very operational or very sort of Roger Penrose-ish. Events in space-time are defined by the coincidence of world lines. World lines in physics carry energy and momentum. Okay. But in special relativity, you can forget the energy and momentum that those world lines carry and just talk about events without reference to the properties of the particles that define them, and, for example, transform those events under the symmetry algebra. Okay. It's not obvious that that should be true in fundamental physics, and we'll see it might not be true. Yes?
So a naive person would, if you had a curve momentum space, you would just naively just take a Fourier transform. What's wrong with that way of going from space-time to momentum space?
That's fine. That's fine. That's fine. And to do that, you need an h-bar.
Oh.
No, there's a question there, which is if there is to be invariant, and if p is non-linearly transforming, then what happens to x?
And what happens to x? And that's, we'll get there. Okay. And you in the paper with Zhao and Kimberly addressed this issue. I come to the same conclusion from a different point of view. Okay. So these are the questions I want to raise. Now, let me just mention where this kind of thinking comes from was the idea of realizing this idea of deformed or doubly special relativity. And the idea was to start very simply and write down some principles that extend Einstein's principles of special relativity. And then the hope was that it was just going to be, simple, as Faye pretends her work just now was simple, to derive the consequences. And that extension of special relativity kept the first two postulates, added the constancy of this energy, that is, and I've already really incorporated that. I've said I'm interested in physics on this curved momentum space with an invariant mass scale. Okay? And then I can relax the idea that c is the universal speed of photons. Since I have an invariant energy, it only needs me the universal speed for E, much less than E Planck. And in some sense, the whole issue that this talk is about is why this was not a homework exercise, if you will, just to work out the physics of this set of constants. Okay, and that is, we're still, as Daniel, as you point out in your talk, we're still, a decade later, worrying about simple things like, can these postulates be consistently realized? Are they consistent with observations? And the point is that all the issues, or many of the issues about realizing these come down to locality. So let's talk about locality. Okay. Now, there are different formulations, approaches to DSR. With DSR1, DSR2, DSR15, whatever. Zhao and I started with one in which the basic idea that we tried to implement was that to go to space-time was that the metric on space-time became energy dependent. And the sort of philosophical point of view, from the point of view, everybody's saying in this meeting when they want to say something impressive that is from the point of view of a particle physicist. So from the point of view of a particle physicist, all physical quantities run, all couplings run, and the metric of space-time in an effective field theory is just a bunch of coupling constants organized in a matrix, and they should run. And they should run in terms, and they should run means that they're dependent on energy scale, and that's really the point of view that we took with Zhao. From the point of view of particle physics, is that the metric of space-time in an effective field theory point of view are coupling constants and therefore should run. Just for fun, when I started to think recently about these problems, I thought I would take a different point of view, which is the point of view called Capel-Poincare, which is a point of view connected with non-commutative geometry. And this is really just for fun. I only have time to do one thing here, but much of what I have to say can be expressed in the other point of view. And indeed, if Jurek and Michaela ever publish this great paper they're working on, they will show that there's an energy-dependent metric which is equivalent to the formulation of Capel-Poincare. Okay, but that's their work, so I can't talk about it. Yes?
When you say energy-dependent metric, energy of what? In particle physics, coupling constants run, but they run with the center of mass.
Of course, that's an important question. And in the framework that I'll look at here, which is based on the free relativistic particle, we're starting with the phase space of a free relativistic particle, and in the phase space there's an energy and momentum of that particle, and I will mean that.
But that is frame dependent.
Of course it's frame dependent.
So
And we'll see.
How can you run?
Well, I'm not presenting. I was just giving you an overview. I'm not presenting the energy-dependent metric point of view. Okay. I'm presenting the Capel-Poincare, and the reason is that this is the framework that was best developed. There are the most papers about this, the most work done to realize in the context of quantum field theory. And I thought if I was going to try to address these conceptual problems that Sabina had raised, it would be safest to work in the best developed formulation. Right? One of the things that we know about Capel-Poincare is we know that it arises in 2+1 dimensions as the effective non-commutative space-time geometry in quantum gravity coupled to particles, coupled to matter. And that's work of a number of people, but particularly Levine and Friedel. And so there really is a interacting theory, which happens to be a quantum theory of gravity, which realizes this. Okay. So I thought it was the safest point of view to start working with this. Okay. But I don't mean to be exclusive. Okay. So I have to show you a little bit of mathematics, not hopefully very much, and then we can get to the fun stuff. So de Sitter space, momentum space is a de Sitter space. I picked some. There are different coordinates you can pick on it. I happen to pick these coordinates, pi, p0, which is minus the energy, of course, where the metric looks like this. The energy-momentum relation, that is the mass shells, then look like this. There's some nonlinear functions of spatial momenta and energy. This is invariant under rotations and boost transformations because this is just mass hyperbola in de Sitter space. One can define the space-time coordinates as linear combinations of the 4 remaining symmetry generators when rotations and boosts are taken out. Okay? I happen to coordinatize those by things I call xi and t. X with p has a commutation relation which is deformed. T with p not so. As I said before, x with t has this funny commutation relation proportional to x again. And with the particular coordinates I've chosen, t commutes with p.
T0 is restricted to positive, or it can go to negative?
It's not going to matter for, if you need it restricted to positive. I'm not doing quantum field theory. You can also choose other coordinates. For example, there's a coordinate capital T which is related to little t and x dot p in this way, okay, which commutes with the xi. So if you are thinking quantum mechanically and you're thinking of a relativistic particle and you want to make a basis constructed by diagonalizing a commuting set of operators, you would probably diagonalize x and capital T and find a basis rather than x and little t. So, and the physics, of course, the questions you ask, the answers can depend on which time coordinate you choose. Okay? And I could talk for the whole day about the mathematics of Kappa-Poincare, but I'm just going to tell you the basic things that come out of studying it. Okay. So what one can do, and this was certainly not original with me, is you can do a constrained quantization of this phase space. The energy-momentum relation taken to be the Hamiltonian constraint. Okay. You can construct wave packets, Gaussian wave packets in the momentum space, and you can propagate them in either of the time coordinates and study what are the implications. Okay. And skipping the mechanics, the results are, if you propagate in the commuting time coordinate, that you get an energy-dependent phase velocity for massless particles. As far as I can tell, the literature disagrees. Different papers disagree with themselves. Anna here has a paper with collaborators where they get a similar result in the non-commuting time, but other people claim it's not there, and I don't have, and I haven't been able to resolve the discrepancy. But another thing that one gets in either time coordinate is an anomalous spreading of the wave packet. That is, the width of the wave packet, which starts off as delta x, grows as you propagate. X is either x or t, is a proxy for how far you propagate it, and grows like this. So for x large, the width grows, and I want us to pay attention to this form, like the Planck length times how far you propagated over the uncertainty in position, or equivalently times the uncertainty in momentum. Okay. So there is a stochastic component which grows with the product of uncertainty and momentum, Planck length times x, as well as possibly an energy dependence to the speed of light. Yes?
MP is the same as your E capital T in the momentum space, or?
Yes.
It's exactly the same.
Yeah.
So why it's stochastic? Why it's not quantum mechanical?
Well, quantum mechanical. The wave packet is spreading. Okay. And this is, this talk is not about that, but this is relevant for the analysis of experiments. Okay. Although as several people, including you, will tell me before we can analyze experiments, we have to understand what space-time is. Okay. So now I address the issues, the issues of the talk, the problems with non-locality. And the uncertainty relation you can derive from this commutation. I mean, as soon as you know that you can't diagonalize the time coordinate and position coordinates, you know you don't know what an event is, and that is irritating. Okay, because an event, according to Einstein, has a definite t and a definite spatial coordinate. If they don't commute with each other, there's an uncertainty delta x delta t is greater than the Planck time times the distance in x. And in the literature, there is a certain complacency in not everybody, but some papers in which people look at that and they see the Planck time there and they say, oh, that's a small effect, that'll be just messed up with quantum gravity and fluctuations of the light cone, so we don't have to worry about that. And then there are other people who see the X and say, oh my God, what's happening? You have an uncertainty which is growing with X, so what happened to homogeneity? What happened to translation invariance? And even if TP is small, the product of TP times X can be large when X gets large enough. So your ignorance about what an event is can grow as you go to large distances. So that's the signal that there is a serious issue with locality here. Okay. Here's another way to see that there's an issue with locality. And this starts to be stuff which is in the papers of mine.
I have a question. How do you know you are dealing with an issue of locality if you don't know what's the relationship between T and X?
Absolutely. Thank you for that. I will address that. Okay. So, interestingly enough, the symmetry algebra, and this is the work of Jurek and Michaela, the symmetry transformations, these are the boost transformations on X and T, these are the infinitesimal boost transformations to first order in Planck time, or 1 over the Planck mass. It mixed position in time with energy, angular momentum, and momentum. So what I was saying before is true. You don't, if you have a world line and you want to transform an event on that world line, where that event goes in X and T depends on the E and P and angular momentum carried by that world line. This is a feature of this. Now, Florian emphasizes to me that in the very mathematical Kappa-Planck array, half algebra, blah, 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 there may be a mathematical way around this that I don't understand, so I'm just pointing to what Florian pointed to me yesterday. But this is what happens if you take the generator of boosts, which comes from the symmetry algebra on the curved momentum space, and take it to generate transformations by commutators in the standard way.
Isn't it, not to press the point, exactly a statement saying the metric affecting it?
Yeah. And this is what you and Kimberly and Zhao got. I don't know if they're precisely the same formulas, but they're the same kinds of formulas. Okay. Let me emphasize, it's not just boosts. Translations in Kappa-Minkowski space, if I make a translation with a spatial translation AI, I get a change of the time coordinate which involves AI dot P. Okay. So I have an event and I'm looking at it in some frame and I just translate the frame. The coordinates of that event are split according to what is the energy and the momentum at that event. Okay? So the question is, okay, we have a situation, if we take the point of view that Einstein tells us, that events are defined by coincidences of world lines. If we have an event defined by a coincidence of several world lines in one frame, and we describe that same event in a frame which is either moving with respect to it or translated with respect to it, it's split into several events, like that. So something like that, say a scattering process, 2 in and 2 out, in one frame of reference looks like that, in another frame of reference. Okay. And so the question is that real? Or is that a coordinate artifact? That's the question. Okay. Now let me know if the differences are always proportional to the Planck length or time times a position or time coordinate times the velocity of the moving frame. This is in the case that that it's a Lorentz boost times the energy over h bar. Okay. Now, again, you can stare at the TP and say, oh, these are tiny effects that will be smothered up by quantum gravity, but you can stare at the product of these things, and you can argue that when X is cosmological, and why not, then this becomes a macroscopic time or spatial difference. Also, these splittings, you can check it, can be time-like, which means that you can argue about whether this event caused this event or this event caused that event, and who is to the future and who is to the past. depends on the direction of motion of the moving frame. Yeah, let me, because I am running short on time and I'm only just introducing the, okay? Okay. Now, Sabina's vivid paper made the argument that if DSR is indeed frame independent, then you have to take this seriously. That is, you can't say, oh, in the stationary frame is the right description where the events are real events as Einstein taught you, because if we really believe in relativity of inertial frames, this description has to be as good as this. Since these can be macroscopic, if the event is a cosmological distance away from the origin, then you can bound the parameter in here, and the parameter is the Planck length. You can bound it, or a number of times the Planck length, by many, many orders of magnitude from the tests of locality coming from particle physics. So this is either inconsistent or it's just irrelevant for nature. It's a description of an extension of relativistic physics which has so much non-locality in it that it just has nothing to do with physics. And that was, and I don't have time to go into her arguments, but Sabina made the point in this physical review letter, and if maybe in the discussion, if we have time, these are the diagrams by which she made that argument. Okay. And I remade that argument in a different framework. And that is in the Kappa-Poincare. So you're not allowed to say, oh, well, it's not the case in Kappa-Poincare because of non-commutativity, half algebras, dot, 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 dot. We know it's okay. You're not allowed to say that because it's easy to reproduce the crisis in the Kappa-Poincare. Okay. So here are the possible responses, and I'll use the remainder of my time to discuss what I know about the possible responses. Good. Okay. So one, I think we have to say this is serious. I don't know how many of you watch The Wonder Pets if you have little kids, but there's this little bird that goes, this is serious in every episode, and this is serious. Okay. If the theory is right, these cannot be physical non-localities. Okay?
What do you mean? So what does that statement mean?
It can't be without, I'm going to address it in these things. Okay, so let me go ahead and address it. At the very worst, maybe I should have said if the theory is right, these probably cannot be physical non-localities. Okay? You can attack the issue on several ways. So let me indicate some ways to attack the issues, and then I have
By
one.
physical, you mean observable, or
Yes.
That's
yes.
the definition.
Yes. Okay. Okay. One, my quantum mechanics help. I spent some time in the introduction to convince you that when we talked about space-time, H bar is turned on. And so maybe the problem is we're making too classical a notion of event. Might analyzing the same issue in quantum mechanics help? Okay. Might the locality be very non-generic? I'll say what that means when I get to it. Might these be coordinate ambiguities of a new type rather than real physical intervals? I'll discuss what that might mean. And the last one I won't discuss is might the problem be that the Lorentz transformation of a composite state involving several particles is not just the sum infinitesimally of the Lorentz transformation on the individual particles, which for the people who know what it means screams coproduct. Okay, so those are possible ways out. There's not a final resolution. I'll discuss each of them in turn. Might quantum mechanics help? Okay. So I mentioned earlier that there is an anomalous spreading of the wave packet, which for large x, that is, if I start a wave packet and propagate it over here, and the origin of my coordinates in my inertial frame is here, and I'm propagating the wave packet to the event here, there's an anomalous spreading which is proportional to the Planck times x times the actually the b shouldn't be there, apologies, times the uncertainty and momentum over h bar. Okay. Might it be, this is the first thought, just naively, that because of the spreading in wave packet, the effect that we're talking about grows as distance times the momentum. So might it be that by the time the wave packet gets here, the uncertainty in the position is bigger than these differences in all cases? Okay. That doesn't prove that there's an invariant quantum mechanics here which resolves the problem, but that would help. Okay. And Sabina investigated this in her paper. I investigated this. It's hinted at in other papers. And it's a near miss from my point of view. That is, the spreading of the wave packet doesn't grow proportional to the momentum of the particle. It grows proportional to the uncertainty in the momentum of the particle. And you can choose wave packets so that the uncertainty momentum is greater than the momentum. And then the uncertainty, the quantum mechanical uncertainty hides this non-locality, but you can choose other wave packets where it doesn't. Okay. So quantum mechanics helps, but it's not a slam dunk. It seems to contribute to helping, but it doesn't resolve it. Might the required non-locality be very non-generic? So here's what I mean by this. Let's start with the description of the event in the moving frame. Let's suppose we had a physics where every time there were two world lines in and two world lines out carrying energy and momentum such that the appropriate conservation laws were satisfied, there could be an interaction involving these four events, even if they weren't at the same event, no matter how far separated they were. Okay? How might you argue that? You might argue that by saying, well, there might be a Poincare transformation in kappa Poincare that would take this generic case of four events on four world lines to a single event where those four world lines intersected. Or you could ask even more generally, without fixing these four events, just if you had four world lines in Kaplan-Minkowski space-time, is there a symmetry transformation that takes them all to intersect with each other? If that's the case, then the issue of non-locality is generic. That is, whether four world lines are intersecting or not is completely dependent on the inertial frame of reference. Okay? Well, it turns out that it's not generic. Okay? That is, you will not be able to take four arbitrary world lines or three arbitrary world lines and make them intersect by a symmetry transformation. The details are in the paper. Okay? So there's a less strong argument from the case that we know in observations in particle physics that this doesn't happen to the case that this kind of non-locality disagrees with experiment. And there are details to be filled in, but it could be much worse. That is, you might try to develop a notion of locality in which there was a generalization of locality of the form of, if there is an inertial observer that sees the world lines to coincide, then they interact. And you wouldn't predict that every pair of particles in nature would be interacting. So there might be some mild, relatively mild extension of locality. That needs development. Okay. Third idea, and last one that I'll discuss in detail. Might these be coordinate ambiguities rather than physical intervals? Okay. So I'll give two kinds of arguments for this. One is, just a priori, they look like coordinate artifacts. They only affect observations very far from the observer. Okay? Because there's always the product of x times the Planck times some energy and momentum.
And v.
Times v, right. V is bounded by 1 still. So who is to the future and who is to the past, as I said, depends on the direction of motion of a distant observer. So if this was a real physical non-locality, causality would be observer-dependent in a way that I think nobody wants to contemplate. That is, an observer moving this way towards some gamma ray burst would see some event, the cause of another event, where an observer moving this way away from the gamma ray burst would see them the causal order different. I'm almost done, so let me, okay? So I would, these smell more like coordinate artifacts than real physical non-localities. But how could you really argue that? Okay. So here's a way to argue that. The way to argue that is to go back to something that we all learned and we've all taught, which is Einstein's very operational notion of what the coordinates of an inertial observer are. I mean, look, Einstein told us that what's an inertial coordinate system? It's some observer who is assumed to be locally somewhere with a clock. And they have a world line, and events on the world line are defined to be at 0 spatial position and at a t defined by the ticking of the clock. Every event distant from the world line is assigned coordinates by a physical process of exchanging light signals, in which you send light signals, they send them out, and they come back, and they're the standard formulas where we attribute space and time coordinates to an event by virtue of the time that the light signal departed and the time that the light signal returns. Okay. Now, what I'm going to argue is that because of the anomalous spreading of the wave packet, there's an intrinsic limit to how far away you can successfully employ this process, okay? Assuming that there's some frequency omega 0, that's the accuracy to which you want to synchronize the clock. That is, if I say not just that I want to synchronize clocks, but I want to synchronize 2 clocks to a frequency omega 0, there's a distance after which you won't be able to succeed in doing that.
Where are the 2 clocks?
Here and a clock at some distance. So to synchronize a clock would be to give time coordinates to more than one event here. It's just a repeated case of this. Okay. So I need the return time, the uncertainty in the return time to be less than the inverse frequency that I want to synchronize the clocks to. Okay. Then, and this is just a very simple argument, then I remember that I start with the wave packet here and send it, and it spreads out, and then it keeps spreading out and comes back here. And the width grows like the ordinary width of a Gaussian wave packet plus this term which comes from the non-commutativity or DSR more generally. Okay. Now you can make 2 statements. Okay. And I'll make these statements and then I'll stop because there has been some interruption. One, if I just don't think about energy and I minimize the uncertainty, the minimal uncertainty in the wave packet is the square root of the product of the Planck length and the distance that you travel. Okay. And that gives me a distance x that I can't have the event out. If the event is further than that, then I have failed to synchronize the clock here or failed to give this space and time coordinates to within an accuracy of omega 0. And it goes like 1 over the Planck length times omega 0 squared. Okay. But you can get a little better than that because actually, if you go far enough, you don't get the minimal width of the wave packet. If you travel long enough, this term will dominate if x is long enough. So what you should really do is compute the width by the dominance of this term, because you're asking how large can x be. And then you pull out this term and you get a limitation which goes like 1 over omega 0 times the uncertainty, the original uncertainty momentum in the wave packet. So this tells you that there's a limit which is growing again in the right way in how reliable are the coordinates attributed to distant events. Okay. Now, this is not a proof that the issues that Sabina is talking about are the issues that I raised by generating non-localities with Lorentz transformations are just a coordinate artifact, but it is a simple argument that they might be. They might be coordinate artifacts. As I said, the issue is unresolved. Now I'm going to skip a little bit and go to the conclusions. As I said, this is serious. And the conclusions are, my quantum mechanics help. It seems to help, but it doesn't resolve the problem. Just spreading a quantum mechanical wave packets doesn't resolve the problem generically. Might the required non-locality be highly non-generic? That is, might it be that the kind of non-locality, non-local effects or correlations would not be those that might have been tested for, because they would be highly special, highly fine-tuned? Yes, they are highly fine-tuned. So there's a weakness in the argument that we can already physically bound the parameters of this theory. Might these be coordinate ambiguities rather than physical intervals? So what I'm proposing, and it's only a proposal, it's not an open and shut case, that there's a new, just like in general relativity, there's a limitation to how big an inertial observer can construct a coordinate system, which is the curvature, that in this kind of physics, whether due to the non-commutativity of space-time or the energy momentum dependence of the metric, there's a limit to how large an inertial frame can be. And if that's the case, what we have to do is construct the global picture. Just like Riemann taught us how to construct the global picture of a manifold in which we transcend the limitation to how large a Euclidean or inertial coordinate frame can be, there's a need to construct a global picture here. And there's certainly good work to be done. Now, the last point about the composites, really about the coproduct, might the mistake be to transform the pair of particles or triple of particles making an event, to transform them just by transforming each particle independently without taking into account that it's really a composite system. This is an interesting issue and could be investigated, and the mathematics of Hopf algebras allows one to investigate it. So I would encourage people who know that kind of mathematics to look into that. Okay, thank you very much. Any questions?
Yeah, so it's not a question, it's a comment, and Nina knows this anyway, so I'll try to make it short. About the 4 points that you talked about, actually you didn't talk about the last point, and I haven't heard this before, so I have nothing to say about this. So the first point, my quantum mechanics helps, well, you come to the conclusion that it doesn't have a node anyway, but in addition to this, the term that you call the non-locality in your inequality just is not the non-locality, which you can look up in my paper. So that's why your inequality seems to hold in more reference frames than mine does. Then the second point, might the required non-locality be very non-generic? Well, the thing is that your variables accounting of the word lines that might meet in one frame but not in the other would kind of mean that the cross-section, that the probability for an interaction to happen does depend on where and when the particles will reappear, which is kind of weird. Actually, you've come to the same conclusion in the third point, that this mess up of causal order doesn't make a lot of sense. So about the third point, that it could be coordinate ambiguity, so I don't really have the time to go into the details, but the thing is, if you want to avoid that 2 observers in a particular distance can synchronize their clocks to a precision better than the non-locality, you have to avoid this for all energies. So this gives you a constraint on how large the non-locality can be, and you can do this. So this third case, at least that's the status of what I'm at now, does work, but it gives you a constraint on the non-locality, which is quite tight, and actually is tighter than my original constraint in this scenario. So that's kind of the status of this discussion.
So this is an ongoing discussion. Maybe let's see what other people have to say. I do have something to say to that, which was the transparency that I jumped over. We can go back to that. But the dialogue has been very, very useful here, and that's an example of it. So I mean, we could have a dialogue point by point, but I think let's let's see what other people want to say.
Yeah, what I actually wanted to ask, I've seen nicely here, there, that you have a natural coordinate dependent end of space, where, now, what I wanted to ask in these DSR models, which you nicely described, is, I believe there is another constant, which is the cosmological constant. So in other words, it's not only M Planck, it's M Planck and lambda and C. Of course, this creates a complication, because when you have a lambda, then you know that your space-time is not flat. But there, you have the interesting thing that you have an observer-dependent horizon. And your space is restricted inside that. I mean, inflation is the best. Not inflation, very bad. I mean, I know you don't like inflation, but that's another reason why you probably don't like inflation. Then, what you might be getting there is that you might be getting an intuition of why the cosmological constant is a quantum mechanics effect. All right? Because this horizon, you know, naively, you think if you have a cosmological constant and the cosmological constant is very small, your right-hand side of the uncertainty could become small, because the space is 1 over square root of lambda, and if lambda is a very small number of times M Planck square in an appropriate unit, then you get. So my question or intuition, if you like, is that maybe these issues are addressed by adding the cosmological constant not only in your momentum space, which you nicely done here, but adding it somehow, and probably this is this. The bringing quantum mechanics in the game brings you this constant somehow. It's an observer-dependent horizon, so you are in a coordinate-dependent length of space, if you like, maximum length.
So I mean, I think that's an interesting point. I thought a little bit in that direction and haven't made it work. But let me emphasize something. Okay, I mean, there's a way out which I think is too cheap, and which I didn't want to employ. So the way out is to say, in the case where, I mean, Sabina discussed these in the context of a real event with gamma ray bursts setting forth several photons which are then observed on Earth. And you can take the point of view that when these events become problematical, that is so far away that we shouldn't be thinking in Minkowski space-time, we should be thinking in curved
That's right, because they're beyond the horizon. It's like a Swiss cheese thing. That's right.
But it seems to me that's
not what I'm talking about.
The challenge, that's too cheap. The challenge is, okay, does DSR, or more specifically Kappa-Poincare, okay, present us an arena to do physics which is a possible extension of the physics we know, or is it an impossible extension of the physics we know? And I think that these issues are the key issues. I agree that they have been not sufficiently paid attention to. And you know, and another thing to say about them, I mean, you know, a buzzword of non-commutative geometry is, you know, infrared, ultraviolet mixing. Everything here is infrared, ultraviolet mixing. Yeah. You know, LPX. Okay, everything here is infrared, but infrared.
I mean, lambda is the infrared length, and Planck is the
infrared. But without trying to take refuge in the value of the cosmological constant, or maybe I'm misunderstanding you, I think the question is this a version of possible physics or not? And I think that the issue of these non-localities has to be resolved in order to say that this is a version of possible physics. Yeah, Tom?
So the commutator algebra here, what are the Casimir invariants for this theory?
There's a, I showed that on an earlier slide. There is the Casimir.
There's only one? There's nothing with the boosts or rotations?
Oh, sure. No, sure. They're conserved generators. Yes. Yes. I don't happen to have these on the slide, but there are conserved generators of boosts and generators of rotations, and they do form an algebra. And some people, for example, Florian there knows a lot more about that algebra than I do. Maybe I could just write it down for you later, since we don't have a blackboard. Yeah.
I think this idea of trying to pin up what's the space-time in this setup is very good. But what I'm concerned is the jump between notions of space-time associated with double special relativity and the intuition we get from notions of space-time that are from our ordinary setting. For example, you said X is large in cosmological situations, but how do I know X is large in cosmological situations? The X that you have there is this X that is measured by double special relativity. It's not the X that I have learned how to measure. You said velocity has to be smaller than light, but that we infer from special relativity requiring the preservation of the chronological order of cause and effect. If we are going to give that up, then I can no longer say that B has to be smaller, that B has to be bounded by C. And moreover, what is an inertial frame in this thing? All this is supposed to be held in an inertial frame. How do I define an inertial frame? How do I find what is such a
Thanks for
thing
finally
in this
asking a question I can answer. An inertial frame, I would claim, is just what it is in special relativity. It's an observer according to which a free particle moves with a constant speed with no
But
acceleration.
to know what is that, I need to know what is distance, what is time, what velocity.
Absolutely.
I cannot
Absolutely.
obtain before I know how to measure.
No. So my point, so I agree with you. All of these are questions. I don't claim. I'm not giving you the alpha lecture on Kaplan-Minkowski space done right with the physical intuition all there and the operational stuff all there. All I'm suggesting is that if we go back and start to think operationally about what coordinates mean in inertial frames, and apply them to this case, we discover that they are subject to an uncertainty relation, and we had better take that into account in drawing conclusions from functions of x and t.
That's why I said that I'm very happy that you investigate this. But it's very important that when you do it, you keep to the rules of the game from the beginning.
I agree. Fine.
So in the Kaplan-Minkowski case, there exists a choice of coordinates where the momentum is transforming linearly, and the coordinates are also transforming linearly. The multiplication is at the multi-body systems, and there is a coproduct structure and so on. So in this case, do you think that all this non-local stuff is going to appear if P is transforming linearly and positions are transforming in the usual way?
Yeah, very good. Very good.
So if it's fine, then maybe those arguments are a way to specify a choice of coordinates. I mean, to say that maybe this choice of coordinates where momentum is going to transform linearly, and so maybe you don't have this non-local problem, is the right one.
So let me say a few words to amplify your point, and then say what I think is the question. Okay. So kappa, the algebra of Kappa-Poincare algebra and the Kappa-Minkowski phase space that it is the symmetry algebra of are nonlinear, and therefore one can make nonlinear choices of coordinates. One has a larger coordinate freedom in the phase space than we usually use in special relativity. Okay. And you can use that to hide these effects for the one particle case. Okay. And I should have said that, and of course you're right. And then they go into the coproduct, which is the coproduct is the structure of how you act with the symmetry generator on a direct product, or on a direct product of more than one particle state. And there are 2 points of view about this freedom. One point of view is that, and I think that the people in the field, as far as I can tell, are split. One point of view is that everything should be invariant under this larger group of transformations. So all the physics should be invariant. Another point of view is that no, one set of these momenta and energies are really physical. And the way that would be said is that in the quantum mechanical case, that the transformation between the Hilbert spaces that diagonalize the different choices of bases are not unitarily equivalent. They diverge in the infrared or something like that, so they're not unitarily equivalent. And my understanding is that the issue is not resolved. If they're not equivalent, then they're not equivalent, just like different coordinate systems in curved space-time.
My point is that there exists a version of DSR where I think that you don't have all these non-local issues.
Yes. Yeah.
So it's not that people are ruling out DSR, because DSR means many things. I think each one has got its own definition of DSR.
So if you So you know, somebody asked me about n equals 8 supergravity. Okay. Why I didn't work more, I worked a bunch on n equals 8 supergravity. Why I didn't work a lot on it is I prefer to work in the ordinary theory where the problems occurred at leading order and not at fifth order or seventh order. And I feel like about that here. Okay. The problems here are generic. Okay. Sabina's paper is not in a sophisticated mathematical framework. It makes some simple postulates, which I think many of us would agree with, and it derives that there's a description of an issue which is a problem. One can say, yes, there are versions of DSR where the problem doesn't appear, at least as far as we've looked at it. And then I would challenge you to really understand, you know, well, probably you also don't have an energy-dependent speed of light, so you don't have any interest in physics. Yeah, so you don't have any interest in physics at all.
Well, point of view.
I think we should kind of.
Anyway,
this could go
what
on.
you said is not true. I mean, you have scattering, non-trivial scattering, and I mean, you have non-convertible
Okay.
Okay, so anyway, Jal, let me just close. I think that there's a challenge, and you should take up the challenge. Because if you can make a description of the process of gamma ray bursts, gamma rays being emitted in a gamma ray burst and then being observed, and use your co-product structure and investigate how that works, okay, and show that the problems are really resolved in a way which is observer independent, that would be great. But you can't just say, oh, there's no problem.
I didn't see that.
Okay,
That was
wait.
my question.
Yeah. So one last question, because we should really.
Can I just comment on
Yeah.
this?
Okay.
So the thing is that the scenario that I looked at does not rule out DSR, and I said it rules out DSR with an energy dependency on light. So if you don't have an energy dependent light, you have no problem.
Okay, Stefan?
Yeah, I just have a simple pedagogical question. Normally in interaction vertices, if you allow for virtual processes, you know, things can get interesting. So is there a way, or maybe you already did account for that when you talked about the spread of the wave packet? Would that be an example of accounting?
What I was, not from virtual process, but what I was hoping, okay, was that generically the wave packets would spread so much that it would be plausible that in a correct quantum mechanical treatment, there was no known locality of the particle physics types. That is, the vertices were all good local vertices in the usual sense. And the conclusion, neglecting the things that Florian talked about, which are very important, which is how the co-product acts on interactions, which I have not investigated. So, and it may be that that's the key, but having not investigated that, the quantum mechanics by itself does not seem to, it goes in the right direction, it scales the right way, but it still does not resolve the problem for all of the quantum states.
Okay, I think we should thank the speaker again.